Hello, this is Jack Jackson. In this video, we're going to introduce symmetry. Actually, in my playlist, the previous video is an older version that uses some geometers sketchpad. It has a few illustrations and things that we're not going to be doing in this video. And this video more closely follows my current version of the notes. Symmetry is used in art and design. It's an important concept related to transformations. Um, and we're going to be talking about that a little bit here. Okay, first of all, when we want to talk about fixed points versus symmetry. So a fixed point of a transformation, we're talking about a point whose image is itself under the transformation. The image point equals the pre-image point. They're the same thing. So this is a point that is not moved at all when you do the transformation. So notice this is considering those points as individual points. However, sometimes we can also talk about a transformation, which although it may move points around individually, it leaves a certain set of points invariant. Such a set of points has symmetry with respect to that transformation. So it may be that you take an object, you reflect it, individual points are moved around, but in the end, all of the points collectively are the same set. So here's a definition. If a set of points S, which is a subset of the domain plane of the transportation T, is such that its set of images equals S, then we say that S is symmetric with respect to that transformation. One way to say that symbolically is T of the set S is the set S. What do we mean by that? What we mean is T of all points A, the set of all points A in S, okay? We take all their images, take that set, and that's what's meant by the left side, and that's equal to S itself. The set S may or may not contain points which are individually fixed by the transformation T. So, for example, we've already studied this for each transformation, but recall, for example, that the only fixed points in a reflection are those on the line of reflection, the mirror line. These points are individually fixed. However, if collectively the points in the image are the same as the points of the pre-image after reflection, the total figure remains the same as the set of points, then we say that figure is symmetric with respect to that reflection. For example, as y equals x squared has reflective symmetry about the y-axis. So here's a graph of y equals x squared, and notice that the point 0, 0 is fixed, but the point 1, 1 moves to the point negative 1, 1, but that's a point in the set, and the point negative 1, 1 gets moved to the point 1, 1, but that's a point in the set. Everything in the first quadrant gets moved to the second quadrant, and the second quadrant gets put right back on where the first quadrant was. When the dust settles, the same set of points is exactly the same. A geometric figure which has symmetric with respect to a reflection about a mirror line is said to be symmetric with respect to that mirror line or has line symmetry about the line. Our bodies have approximately, but not exactly, three-dimensional symmetry about a vertical line or plane. Okay. Likewise, the only fixed point in a rotation is the center of the rotation. However, collectively, the points in the image are the same as the points in the pre-image. The total figure stays the same. After a rotation, we say that a figure has symmetry with respect to that rotation. For example, y equals x cubed has 180 degree or pi rotational symmetry about the origin. If you take this graph and rotate it about the origin, pi radians or 180 degrees, half circle rotation, the point in the first quadrant land on exactly the points in the third quadrant, and the third quadrant points land exactly on the points in the first quadrant. The only point that's individually fixed is the origin again, but collectively the points stay the same, so that has symmetry with respect to that transformation, that is, rotational symmetry of 180 degrees about the origin. A geometric figure which is symmetric with respect to rotation is said to have rotational symmetry about the center point of the rotation through the angle of rotation. If a figure has rotational symmetry about a point through an angle alpha, then it will also have rotational symmetry about the point through angles n times alpha, where n is an integer, in other words, integer multiples of that. So for example, if it has rotational degree, symmetry of 60 degrees, then it'll also have rotational symmetry by the same center of rotation, twice that, 120 degrees, 180 degrees, and so forth. If a geometric figure has 180-degree rotational symmetry about a point, then we say the figure is said to be symmetric with respect to that point. A graph which has 180-degree rotational symmetry about the origin is said to be symmetric about the origin or have origin symmetry. Note that for a translation, there are no fixed points. However, if collectively the points in the image are the same as the points in the pre-image, the total figure stays the same after translation, then we say the figure has symmetry with respect to that translation. A figure with this property will have to be infinite in length. One example is that any line has translational symmetry about a vector parallel to the line. You're just sliding the line along itself. Since there are infinitely many points there, not only infinitely many points, but infinite length, that's going to still end up with the same line. A function which has symmetry with respect to a horizontal translation is called periodic. The amount of translation that results in a congruent collective image is called the period of the transformation. And one very important class of figures with translational symmetry that you've studied are periodic trigonometric functions. For example, think of the graph of a sine wave, which we see below, which repeats the same pattern forever. The figure is periodic with period 2 pi. So if we translate this figure to the right by 2 pi, this piece right here will end up landing on top of the piece. This piece from 0 to 2 pi will end up landing exactly on top of the piece from 2 pi to 4 pi. And that piece will go on to the next. Well, since it goes on forever left and right, collectively we end up with the same thing. So we would say it has symmetry with respect to that translation. More often we would just say this is a periodic function. And of course, translating by any multiple of 2 pi will also get us the same thing. So if we take this piece from 0 to 2 pi and shift it by 4 pi to the right, then it lands on this piece from 4 pi to 6 pi. Okay? And so forth. We can shift to the left as well. One of the main reasons for studying trigonometric functions is to use them to model periodic behavior in the world. This includes cycles from night and day caused by the rotation of the Earth about its axis, the seasons caused by the revolution of the Earth around the sun, tides caused by the revolution of the moon about the Earth, waves, sound waves, uh, electromagnetic waves, and so forth. And so these types of things that we want to study, they affect all kinds of other cycles on Earth in our lives. And so uh, we will, lots of things go in cycles, and so therefore trig functions are useful for studying those. So here is the next little exercise I'd like you to try to do. Take these figures here, equilateral triangle, isosceles triangle, square, rhombus, rectangle, parallelogram, kite, a regular pentagon, a regular hexagon. Make a general figure of that in GeoGebra and create the lines of symmetry for that, for the mirror lines for reflective symmetry, and show the center and the amount of rotation for at least the smallest uh, rotational symmetry. And by the way, if every figure, if you rotate pi 180 degrees about that point, will end up back where it starts, that's not considered symmetry. There are a lot of interesting transformations in art. Some artists have been able to use geometric transformations to create some very interesting graphics and artwork. Transformation and symmetry are often used in commercial art and design, as well as in fine art. And I want to lift up just a couple of artists that make use of transformations and other mathematical ideas in their work. One is Scott Kim. He's a living artist as of this video. Um, Here is a website for him. He has some very interesting graphics created with text and symmetry. And here's a couple of examples. He modifies the fonts and to the point where he can get things to have some symmetry within them that they would not normally have, but where they're still recognizable as text. So if you read this, can you read what this says? Hopefully you can recognize that this is uh, mirror, but it also has a mirror symmetry, a reflective symmetry about a vertical axis right through here. So if you held this up to a mirror, it would look the same. This one says Ventura. Hopefully you can still recognize that as saying that word. But if you there's a center point right in here somewhere that if you rotate this 180 degrees, clockwise or counterclockwise, um, it reads the same both ways. Reads this way, Ventura, or rotate it around, it reads the other way. So he has all kinds of cool stuff like this that he's done. I think it's kind of fascinating. And he's been creative with putting these together. So I encourage you to check out his site. Probably the master of fine art using mathematical ideas, including some transformations, is M.C. Escher. Here he lived from 1898 to 1972. Here's a website for him. He was a Dutch graphic artist who incorporated several mathematical concepts in his art, including symmetry, transformations, and tessellations, Mobius strips, um, different 3D and 2D shapes that are common in mathematics. Again, I strongly encourage you to go online and search for some images. Here's just a few examples. Uh, Notice this as a tessellation, and you can see how this has sort of been morphed from the landscape here, a farm perhaps, moving into birds going, white birds going left, black birds going right, and there's some mirror image in this as well, some reflective symmetry. Okay, this is a modification of a tessellation. Here's an example of what's actually a tessellation using seahorses here, where we take one figure that tiles the plane. Here is a sort of a tessellated Mobius strip. Mobius strip is a fascinating uh, object that's a two-dimensional object pulled into the third-dimensional object to end up making it have one side. If you're following around this side here, it goes around this way, and just going around here, it's the same sort of inside and out. Has one side to it, one edge. This is a self-portrait, but he did it through a sphere, and so you can see some spherical transformations going on there. This is one of my favorites. I have this one in my office. Actually, both of these two in my office. Um, this is prints of these. This is hands drawing hands. This is a tessellation of reptiles that come to life on the page. And he has many, many more, lots of interesting things, some interesting architectural kind of look things, other shapes. So I encourage you to get online and see some of his work. As I said, I have several Escher prints in my office. I have books of art and graphics of Escher and Kim in my office, and you can come by to check those out if you're on campus.